Great. So it's our pleasure to have Professor Mikhail from the University of Wisconsin-Madison. So Mikhail is the Jack St. Clair Kilby Associate Professor at EECS sorry, Electrical and Computer Engineering and ECE, I guess, in University of Wisconsin-Madison, and he's also jointly affiliated with departments of physics and material science, and other institutes at Wisconsin as well. So Mikhail is this very kind of rare physicist who's very kind of applied-minded, and but at the same time he really understands the basic physical phenomena that is really going on. He's worked on a wide variety of things, not least, for example, how to kind of use metamaterials to change how light interacts with matter, how light kind of reflects off of surfaces, and he's done very fantastic work recently on thermal radiation. So without further ado, let me welcome Professor Katz to our condensed matter seminar. So it's all yours now.
Yeah, thank you so much, Justin. So my sound is good, my video is okay?
It's great, it's fantastic.
Great. Yeah, thank you so much to all of you for coming and for welcoming me, I guess, remotely to NTU. I'm very thankful to Justin for this invitation. Justin and I have had many nice conversations over the last, I guess, 6 or 7 years, including a nice collaborative paper, I think, in the very beginning of my assistant professorship when I started at UW-Madison, and I think right around the same time when Justin was starting over there. So I hope that perhaps these conversations can also lead to some sort of future interaction and future collaboration. So it's really great to be here. I wish it could be in person. Alas, I'm sitting here in my bedroom, but that's how it goes. So before I get started, I wanted to just share a little bit about my group at UW-Madison. So these are some nice pre-pandemic photos. So these are all from 2019. And this is a little bit larger than my actual group. The group is about 10 people. This includes kind of partners and other family members and so forth. And so, of course, over the last year, everything has been as remote as possible and a lot of Zoom meetings, but this is what the group looks like now, and we're very fortunate to be funded by a variety of federal agencies in the United States and also the Wisconsin Alumni Research Foundation here in Wisconsin. So my research group does a bunch of different things. So I think as Justin pointed out, I'm an applied physicist, and broadly speaking, I work on optics and photonics, ranging from the mid-infrared, where I think I do most of my work, to the near-infrared and to the visible. And roughly speaking, there are kind of 4 research areas that we've been working on over the last 5 or 6 years, and that includes new optical materials, including things ranging from biomaterials to materials with giant anisotropy, to nanostructured materials, to phase transition materials. So I really enjoy working with material scientists and condensed matter physicists, even though I am neither myself. And then, the optical materials work really kind of merges into a lot of applied work that has to do with shaping light with nanostructures. So that means kind of thin films and metamaterials and metasurfaces, work on thermal emission engineering and metrology, so the measurement and engineering of thermal radiation, and then some work in vision engineering, essentially trying to enhance kind of the range and resolution and the spectral resolution of human vision. But today, I'm primarily going to talk about kind of this area over here, thermal radiation engineering and metrology, in part based on some novel materials, but also just kind of some measurement work that hopefully some of you will find interesting. So I also wanted to thank everybody who contributed to this talk. So this work is, of course, in collaboration with many people, including a number of students and other trainees in my group, some collaborators at the University of Wisconsin-Madison, as well as external collaborators at Purdue University, the University of Vienna, and the Naval Research Laboratory. I want to, in particular, highlight all the contributions from Dr. Yujia Xiao, who is a research associate in my group right now and has really kind of taken the lead on a lot of the things that I'm going to show you today. And he's on the faculty job market this year. So if you have faculty openings this year, this is a wonderful opportunity to get a really great scientist at your university. And please let me know if you're interested after the talk. Okay, so here's the outline. And by the way, before I really get going into the science, I want to please welcome anybody to unmute themselves and ask questions at any time. I would love to be interrupted. I think it's much better that this goes as a conversation. If it turns out that that's going too long because of questions, I'll just dump the last topic or two. I'm very happy to do that, and prefer it. So if you have questions, please unmute yourself. I would prefer that to chat because I have full screened my screen and I might not see it if it's in that chat window. So the outline of the talk is, first I'm going to give kind of a brief refresher on thermal radiation, what it is, how it's measured. I'm going to talk about precision thermal radiation measurements under some challenging conditions. So you'll see what that means in just a little bit. But essentially, how do you kind of precisely measure thermal radiation in a typical optics lab? Then I'll talk about a couple new techniques for measuring thermal radiation that I think are interesting and potentially useful. We'll see, but at the very least, they're new and interesting. One of them is depth thermography, which is essentially the ability to measure temperature using thermography remotely, but beneath the surfaces of materials. One of them is Planck spectroscopy, which is essentially the ability to do spectroscopy without any spectrometer components or any optics that provide, any sort of dispersive behavior, instead using Planck's law of thermal radiation. So this is kind of a unique type of spectrometer. And then I'll talk about the use of temperature tunable optical materials for the engineering of thermal radiation. In particular, we're going to talk about vanadium dioxide and samarium nickel oxide, both of which have insulator to metal transitions, which we can take advantage of for thermal radiation engineering. I'll use that to demonstrate a zero-differential thermal emitter, which is essentially an object that no matter what its temperature is, over some temperature range, it emits the same amount of thermal radiation everywhere, kind of over that range, which is a little bit weird and surprising. And then if time allows, I'm going to cover our demonstration of the fastest ever temporal control of emissivity. So essentially the generation of infrared optical pulses by dynamic control of thermal emissivity of surfaces. So here is the kind of the refresher on thermal radiation. Sometimes people call it blackbody radiation, although that's a little bit less general. In general, the spectrum and intensity of thermal radiation is given by Planck's law, which is, of course, the first great success of quantum theory. So it's near and dear to the hearts of many of us physicists and applied physicists. And here is Planck's law, which gives us this general kind of intuition that the hotter an object is, the more thermal radiation it emits, and also the thermal radiation skews towards shorter wavelengths for higher temperatures. And then if you integrate Planck's law over all wavelengths and all emission angles, you get the Stefan Boltzmann law, which says that the intensity or irradiance of thermal emission that is given off a surface is equal to temperature to the fourth to a constant, where temperature to the fourth is, of course, in Kelvin. So here's a plot of the irradiance for a black body versus temperature, and in this case, I'm plotting it in Celsius, but it follows this Stefan Boltzmann relationship. Now, this intuition that we get from the Stefan Boltzmann law that hotter objects emit more light, of course, holds not only for a black body, but also for real objects. And for real objects, we have this metric that we use called the emissivity. In this case, this is the integrated emissivity, so it's wavelength independent, which is for a number that can be between 0 and 1. It essentially encodes the propensity of an object to emit thermal radiation. 1 means it's equivalent to a black body in terms of a thermal emission, and 0 means it doesn't emit any thermal radiation at all, no matter what its temperature is. And so this one-to-one mapping then between temperature and the thermally emitted power, temperature and thermally emitted power, is of course always kind of one-to-one, whether or not you're looking at a black body or an object with some sort of emissivity, whether you're looking over all wavelengths, this integral, or you're only integrating over some sort of wavelength range, like an atmospheric transparency window. And from that, we essentially kind of enable infrared imaging, right? Thermal imaging, because if, for example, you have a surface and it's hotter in the middle and a little bit colder on the outside, it has the spatial gradient, then of course that maps directly into thermally emitted power, and the shape of the thermally emitted power image is going to be the same as the shape of the underlying image. So this is general thermography, infrared imaging to measure surface temperatures. So here's an example. This is these are infrared images of our family dog, Toby, who I just walked, a couple of hours ago. I took the infrared camera home for a couple of days to make these images, and you can see that if you look around his eyes, for example, you measure a temperature that's essentially body temperature, and if you measure the nose of the dog, then the temperature is close to room temperature, or even lower than that. And dogs' noses are kind of famously cold. I never knew why before I got a dog, but we got him about 2 years ago. And if you look very closely, sometimes he will lick his nose. And then the evaporative cooling, because the nose is cold, the evaporative cooling is what cools down the nose. And that turns out to have kind of biological benefits for a dog's sense of smell. So the reason why, the mechanism by which dogs' noses are cold is actually evaporative cooling, just because they lick their noses and it keeps them cold. So this is a factoid that I learned.
I'm sorry, is that color bar there in Celsius or?
Yeah, this is a color bar in Celsius.
So there's a 16-degree difference?
Yep, that's right. Yeah. So the dog's body temperature, I think, is a little bit higher than human body temperature, but not much. I think I don't know if it's 38 or 39 or 40 or something like that. But the nose of the dog is below room temperature, actually, because of evaporative cooling. So the dog's nose is always wet and cold, especially when it's sniffing around. So yeah. And again, before I had a dog, I always knew that dogs' noses were kind of famously cold, but I never knew why kind of mechanically. But then you just watch him and he'll just lick his nose, and then evaporative cooling cools it down. It's quite fun to see how an animal is going to kind of do that self-regulation to enhance its sense of smell, which is very cool. His name is Toby, by the way. So the reason why I'm interested in thermal radiation is because there are really, I'm an applied physicist and an engineer, and I think there's a really nice opportunity for engineering of thermal radiation. So if you take a look at an object which is not a black body, some sort of realistic thermal radiator or just any surface, its spectrum of thermal radiation is given by Planck's law with this wavelength-dependent emissivity correction. This is also a number between 0 and 1, but it is wavelength-dependent, the wavelength-dependent emissivity, which tells you essentially how close is this object to a black body in terms of how much it thermally radiates at every given wavelength. But this parameter doesn't necessarily have to be wavelength-dependent. It can depend on many other things, many other degrees of freedom. So it can depend on direction, on polarization, on temperature, on applied electric field, applied magnetic field, on really kind of anything you can think about. Let me admit another person to the room. This is in fact an optical property of an object. So what's up? Oh, sorry. I thought I heard something. Justin, can you still hear me? I think it was just
a new person. Yeah, I think it was a new person who joined and he didn't mute himself. So I just.
Oh, gotcha. Okay, yeah. I think it doesn't auto mute when.
Yeah. I'm sorry. Yes, I should.
No, that's okay. All good. Yeah. So the emissivity is this optical property of the object, and the reason I say it's an optical property of the object is because according to kind of a fundamental thermodynamics law called Kirchhoff's law of thermal radiation, the emissivity is exactly equal to the optical absorptivity. So if you measure an optical absorptivity of an object, it absorbs 60% of the incident light at a certain wavelength for a certain direction, for a certain polarization, and so forth. Then it's the emissivity at all of those directions, polarizations, and wavelength is going to be exactly 60%. So this is an equality, of course, and this is potentially very exciting because you can imagine making a surface that only thermally radiates in a particular direction, or thermally radiates in the infrared and therefore can cool itself down while, for example, reflecting or being transparent to sunlight. So this is how people make kind of cooling surfaces which radiate into the darkness of space. There's really a lot of opportunities here. If you're interested in some of this kind of emissivity engineering, jointly with Andrea Alou's group, we wrote an article last year in Nature Materials, a review article that kind of described all of these ways of doing nanophotonic engineering of far-field thermal emitters. So I recommend checking that out if you're interested in kind of emissivity engineering broadly defined. So this parameter, the emissivity, can in some cases also be undefined. And one simple example is if your surface or your object can't be defined by a single temperature, it has to be defined, for example, by multiple temperatures. So for example, in the case where the lattice temperature of a semiconductor and the electron temperature are not necessarily the same, then you can't define a temperature, and you also can't easily define a single emissivity. It has to be a little bit more complicated than that. And there are a number of examples like this. And there's also examples when you kind of appear to violate Kirchhoff's law, for example, in the case of non-reciprocal materials, where you have kind of gyromagnetic media and an external magnetic field. So there are certain instances when this, kind of appears to break down a little bit. And long story short, I think it's very useful to have experimental capability to measure thermal radiation very accurately, not just necessarily the emissivity, but really this entire kind of thermal radiation spectrum off of surfaces. And that's important for materials characterization and for various applications like temperature regulation and infrared camouflage and so forth. And so this is what we started doing about 5 years ago when I really got going for the first time at UW-Madison with our experimental work. We really wanted to build this experimental capability. And so I wanted to tell you a little bit about that because I'm an optics experimentalist. And for an optics experimentalist, the concept of measuring thermal radiation, measuring the spectrum of thermal radiation from a surface, sounds like it should be really easy. So in our lab, we have this Fourier transform spectrometer. In this case, it's coupled to like an infrared microscope, so we can look at small samples. We have a temperature stage, so we can change the temperature, going down to cryogenic temperatures or very high temperatures. We have we built a little tilt stage for our temperature stage, so that we can do these measurements at different angles and so forth. And you would think that that would be it, that you would put your sample down at a temperature controller and you would measure the spectrum with a spectrometer, and then you put some sort of a reference, like something that looks like a black body, like for example, this carbon nanotube array that we use, and then you divide the two because you're looking for a ratio, and that's it, everything is fine. And so the question is, is that it, or are there more complications? And of course, as we found out, there are a lot more complications, and I wanted to kind of tell you about some of them briefly. So some of the complications include the fact that the data analysis has to account for thermal radiation, not only from the sample, but of course from the detector and from the optics and from the person that's standing next to the spectrometer. It has to account for the frequency-dependent response of the instrument. It's actually non-trivial to obtain and characterize a good reference, which can also be sometimes temperature-dependent. So there are a lot of kind of interesting difficulties that come up that you would think would be quite easy. And I want to just show you some of them because when I first saw them, I was very confused, and I think it's fun to kind of talk through. So here's an example. What we did is we took a kind of a laboratory blackbody reference, which is a piece of silicon wafer with a vertically oriented carbon nanotube forest on top of it. Essentially, this forest is quite tall. It's about 500 microns, and this thing is more or less a good blackbody from the visible all the way to the far infrared, just because it's a very absorbing layer and it has this gradient index structure, so it's well impedance matched to air, so there's really like no reflectance, and it's very, very black. And so we do this measurement. So we have the spectral intensity that we measure on, our FTIR versus wavelength. In this case, the reason this is in arbitrary units is because this also includes things like the responsivity of the detector and the transmission of the optics. So this isn't really the blackbody spectrum, it's something a little bit different, but it's whatever we measure from the spectrometer at 30 degrees Celsius. Okay. Then we decrease the temperature to 25 degrees, and of course the spectrum goes down. This is totally normal, what you would expect. It keeps going, it keeps going, it keeps going, it keeps going, and then you go down to below room temperature, and the spectral shape starts changing a little bit, which is a little weird because you wouldn't really expect the emissivity of this blackbody reference to change, from 21 degrees to 20 degrees, but somehow it seems to. That's weird. And then you keep going to 19 and to 18 and to 17 degrees Celsius, and to 16 and to 15 and to 10 degrees Celsius. And now we're back to the same spectrum that we measured, roughly speaking, in terms of intensity, that we measured at 30 degrees. So here you have the thermal radiation coming off of a blackbody reference, which goes down with decreasing temperature. And then as you decrease the temperature some more, it goes back up again, which is, well, not what's supposed to happen, right? It clearly violates all sorts of physical laws, which is problematic. And so we spent a lot of time trying to figure out what it was that was going on here, because we knew that this was not physical. Well, we knew that at least it wasn't some sort of interesting physics that was coming from the sample, because we know that the sample can't possibly be changing in this way as a function of temperature over a range of something like 10 degrees. So something was going on with our instrument that we needed to figure out. And what it turned out was happening, which once we figured it out, we published in 2019 in PhysRef Applied, was that there are very kind of strange, non-trivial background contributions to the thermal radiation from different components of our optical setup. So this is kind of a schematic for optical setup. We have the sample, it's sitting on top of a temperature controlled stage. It's sending light into this Michelson interferometer with a tunable mirror. This is our FTIR, and then through some sort of apertures and filters and whatever else, and then eventually to our detector. And what we found is that in addition to the light emitted by the sample in this forward direction, there's also forward propagating background. So for example, if this mirror is emitting a little bit of light, we call that forward propagating background because it's propagating in the same direction as the light from our sample. But it's something that we have to be able to subtract away from our measurement before we kind of are confident that what we're seeing is only from the sample. But then you also have backward emitting background from the detector side. So for example, if you have like an aperture over here and it's emitting thermal radiation, some of it is emitted in the forward direction, and the light that's emitted in the forward direction never gets measured because even though it hits the detector, it doesn't go through the interferometer, and therefore it's not modulated by this moving mirror, and the detector doesn't pick it up. So we have like an AC coupled situation where you have a high pass filter and you just get rid of all of this forward emitting background. But the backward emitting background, the background that goes into this beam path and then is reflected from the interferometer and comes back, that is modulated and that is detected by the MCT detector. And it turns out that it's this backward emitting background that has this kind of strange contribution that results in this effect that the signal goes down and then back up again. That's, though, not trivial at all. And so I want to kind of show you how that works. So here is an experiment that we did. Instead of looking at the Fourier transform spectrum, which is what you would normally do when you look at the output of an FTIR, we took a look at just the interferogram. So that's what the detector over here is reading in volts as a function of the mirror position over here. So this is just the interferogram before you Fourier transform it to get a spectrum. And so what we saw is that at 30 degrees versus at 50 degrees, there is like a phase offset in the interferogram. So it's kind of pi out of phase in the interferogram between the low and high temperatures. And so that's kind of suspicious. And so we did some linear algebra to essentially extract what component of this interferogram that was changing, what component of that was the background, and what component of that was the sample. And the way that we did that is we checked which component was not changing and which component was changing as a function of temperature, because we have all these data sets, of course, individually. And so what we found is that even though in the overall data, you do have this effect where at first your signal goes down with decreasing temperature and then it goes back up again. But if you do this kind of decomposition, you find that this effect isn't here. And in fact, what's happening is you have an out of interferogram phase, background contribution, and then you have a fully in phase contribution to the interferogram from something that's temperature dependent, which pretty much means it has to be from the sample, and that's always only decreasing with decreasing temperature. And so that's good. That's kind of comforting for us. And so we did a little bit of analysis, and what we found is that under kind of straightforward assumptions, for example, assuming that our system is lossless, our beam splitter, our mirrors are lossless, which is almost a good assumption, and then also that the interferometer is symmetric, which means that, for example, for a fixed mirror position X, the forward transmission from kind of the input to the detector and the backward transmission from the detector back toward the input, as long as those are equal, which has to be true if you have a reciprocal system. We don't have anything that breaks time reversal symmetry or anything like that, so or reciprocity, and so this has to be true. If you simply make these two assumptions and you do a forward calculation where you say, hey, if I have a forward source, for example, the sample over here, what does it measure on the detector? And then if I have a backward source over here that's emitting in this direction, and what does it measure on the detector due to reflection from the interferometer, you're going to find, using simple incoherent addition, that what your detector is going to measure is actually the difference between the forward emitting source and the backward emitting source. And this is why we have that minimum right around room temperature from in our measurement, because essentially at close to room temperature, the backward emitting source, which is at room temperature, is essentially canceling out our forward emitting source. And so the reason I told you this story is just because I think it's kind of an interesting caveat that you have to always worry about when you do these thermal emission measurements at temperatures close to your lab temperature, and also because this understanding is really enabling for our calibration of our instrument to enable very good, very accurate thermal emission measurements And as you'll see in a little bit, that's quite important for us. And so this is just an example of the final calibration. So I'm going to make the claim that with good calibration, we can measure thermal radiation with very high precision and very high accuracy, including down to low temperatures. Oh, there's something in the chat. Oh, no, that's just reminding you to record.
Yeah, that's right.
Yeah. So we did a kind of a benchmarking test. So this is the emissivity that we measure using this direct emission measurement from like a reference sample, which is just a flat polished wafer of fused silica, and that's the green curve over here. And this is emissivity at an angle of 10 degrees, but unpolarized. And then the black line that's laying on top of it is ellipsometry data. So we did spectroscopic ellipsometry with our mid-infrared ellipsometers and applied Kirchhoff's law and found that the two curves lie on top of each other. There's pretty much no error bars that are visible. And so essentially, we can use this to obtain very accurate and very precise measurements of thermal radiation from various objects. And this is true whether you can define the emissivity very well, like you can here, or for cases when the emissivity is not very well defined. For example, when your system is not at thermal equilibrium, like it has to be defined kind of by multiple temperatures, for example. And that is also important for us for some of the things that I'll show you in just a little bit. So if this is kind of relevant to your measurements, we actually wrote a quite long paper that's sort of half review article, half original research paper in Laser and Photonics Reviews last year, which gives like kind of a flow chart and detailed instructions and examples on how to do thermal emission measurements in various circumstances. And so if you have like a simple system, you follow a simple method. If you have something more complicated, you follow a more complicated method, and so forth and so forth. So you're welcome to check this out if this is something that you're interested in. Okay, any kind of questions or comments so far? Again, please feel free to butt in at any time and ask any questions.
Yeah, no, actually, I have one small question, but I'm sure you'll address it. In what kind of circumstances will you have two temperatures? Like, is it just when you have some kind of spatial homogeneity, or
So I will show you one example in a second, but there are other examples too. So for example, let's say you have a semiconductor and it's pumped so that you have a lattice temperature and an electron temperature, and they're different. You could have a spatial inhomogeneity where you're looking at thermal emission from a sample and it has one temperature here and another temperature here. You could have a situation when you have a semi-transparent material, I'll show you that in just a second, where the top part is hotter than the bottom part. So there's kind of many situations like that.
Okay.
Yeah.
Okay, thanks.
All right, so let me show you one of those situations. So now that we can precisely and accurately measure thermal radiation spectra, even for non-equilibrium emitters, let's take a look at what kind of things we can do with this ability, what kind of interesting things. And one of them is a technique that we developed, and this is published last year, which we call depth thermography. So the idea is the following. Normally, the way that infrared cameras work, for example, the infrared images of Toby, or dog, that I was showing you earlier, is you're measuring the thermal radiation coming from an object, and you are assuming that that thermal radiation is coming from the surface of the object, and you invert that and you get a temperature, and you're assuming that that temperature is the temperature of the surface of the object. But there are cases when we think we can do better than that, or we can extract more sophisticated information from this kind of measurement, especially if you can do a spectral measurement rather than just use an infrared camera. So the basic idea is the following. Imagine you have a sample, for example, some sort of slab of material that is semi-transparent somewhere in the infrared range. So it doesn't matter where, doesn't matter if it's a wavelength of 2 microns or 15 microns or 8 microns or whatever, but somewhere it's semi-transparent, so it's lossy, but not too lossy. And for example, it has some dispersion like this, where the loss changes as a function of wavelength, right? And you're heating this up in a way that the temperature is uneven. So for example, the temperature down here is T1 and the temperature up here is T2, and there's a gradient of some sort in between. What you can do in principle is you can measure the thermal emission spectrum from the surface. And you should be able to invert this using some sort of algorithm based on your knowledge of the thermal radiation physics and some optical physics. and get the temperature as a function of depth. So you can get the temperature distribution in depth. And of course, if you have like an array, a detector array up here, like a camera that's hyperspectral, or you just scan across the surface, you should be able to get kind of three-dimensional information to the temperature everywhere within the slab. And so the reason you're able to get this, at least in principle, is because you have a piece of the material right here that's thermally radiating and it's propagating up. And by the time it gets up here, some of the light got absorbed, but of course, a different amount of light got absorbed at different wavelengths. And so you should be able to use that information to kind of invert the thermal radiation spectrum into the temperature as a function of position. And so this is what we tried to do. So here is the kind of test setup that we used. Again, we just used a simple FTIR setup with a sample sitting on top of the temperature stage. For our demonstration, we used this fused silica wafer that I was telling you about before, and the fused silica wafer is about 1 millimeter thick. It's convenient because, first of all, if you calculate the optical penetration depth, it's on the order of the thickness of our slab in wavelength ranges that we can measure with our spectrometer, and it also has a pretty low thermal conductivity, which means we're expecting a pretty significant temperature gradient to be established between the heater stage and the air fused silica surface over here, and so it should be able to be kind of easy to measure this. And so this is what we decided to use as kind of our test sample. And so here is the measurement and also the extraction algorithm. So over here is the spectral radiance measured versus the wavelength for an experiment where the stage that was used to heat up the sample was at 300 degrees Celsius. So there, even though it might be hard to see, but there's actually 3 curves on top of each other over here. Or I'm zooming into this little region over here, and you can see the 3 curves. There's a red curve, which is the experiment, and then there's a blue curve and a black curve, and those are 2 theoretical curves. So the red curve is our experiment, and the blue curve is essentially the best fit to that experiment with the knowledge of Planck's law, the emissivity of this fused silica wafer, and essentially fitting the temperature. So essentially trying to fit what is the best temperature that minimizes the difference between the theoretical plot and the experimental curve. And the fit is really good. I mean, if you look at them, they're directly on top of each other. But actually, if you zoom in to this region over here, where the wafer is expected to be semi-transparent to infrared light, and you see that they're not actually on top of each other. The uniform temperature sample is a little bit less spectral radiance, and essentially that kind of implies that there is some part of the object which is at a lower temperature than what we kind of think it is. And so what we did instead is we built a model. Rather, Yuja built a model, which is essentially kind of a thin film model where you're taking this object, which is just a single homogeneous object, but you're discretizing it into many, many thin films. And you're assuming that the optical properties of each layer are the same, but the temperatures are slightly different. And we don't necessarily know what those temperatures are, but they're different. And so what that allows us to do is that essentially allows us to try different combinations of different temperatures of these layers, and then to see if we can match the experimental curve better. And if we can match it better, then we're assuming that this is a better kind of prediction or guess of the temperature distribution than just assuming that all of the temperatures were the same. And the way that this calculation is done over here is using just a thin film formula, just a transfer matrix formalism with including the fluctuation dissipation theorem to essentially figure out what the total thermal emission is going to be if you have different temperature sources at different positions throughout this thin film stack. And so then once you do this inversion, and this is something that's quite difficult to do because this is a pretty poorly conditioned problem, you have to have a very kind of precise and accurate measurements of your thermal emission spectrum, which fortunately we do. But once you do this inversion, it actually works pretty well. So over here is a plot of the extracted temperatures, and the green line is what we kind of naively assume to be the true temperature, because essentially we know the temperature of the top of our heat stage, and we know the air temperature, and we're just assuming Fourier's law of thermal conduction, so we're just assuming that there's a linear drop-off. We don't quite know that that's correct, but that's a guess. And then over here in the circles is the extracted temperatures, assuming a 4-layer model, essentially assuming there's 4 different temperatures and we fit those temperatures. And then in the crosses, we have the extracted temperatures, assuming that it's a linear model. So essentially, we're assuming that it has to be a line. We don't know what the line is, but we know it has to be a line. And so what essentially we're fitting like a slope and an intercept to this curve. But essentially, we think this is a pretty good way to measure the temperatures kind of within the object of a material. Everything seems to kind of make sense and it seems to work. Interestingly, we don't actually know how to experimentally check exactly how accurate and precise these measurements are, because I don't know of any other way other than depth thermography to measure the temperature inside like a bulk piece of material, let's say like 100 microns beneath the surface. I actually don't know how to do that any other way, and so we don't really have anything to benchmark the technique against, but at least it seems like it makes some sort of sense. I will say that presently, this is not something that's easy to use. It requires this very precise calibration, good signal to noise, and at the moment it also requires some reasonably precise knowledge of the optical properties of material, although this limitation, I think, can be overcome by doing more than just one measurement, by, for example, taking kind of ellipsometry-like measurements at different angles and polarizations, and then using all of that information to kind of infer both the temperature and the optical properties using this kind of thermal emission ellipsometry, if you like. But we have not done that yet. Any questions here?
Looks like Paul might have a question.
Yes.
Paul Rikas, you've unmuted yourself. Do you have a question?
I'm afraid Paul's microphone is not working.
I see. Well, okay, fine then. Well, how about you just continue?
Paul, you're welcome to send a message in the chat, and then maybe either Justin can read it for me, or I can check out the chat if your microphone's not working. We heard something.
Okay, sorry. Maybe I'll just try with the chat.
Oh, it's working now.
Okay, sorry about that. So I was just wondering what the temporal resolution of your setup might be, because I was thinking it might be interesting if you could do like some measurements of relaxation to non-equilibrium steady states or something like that.
Yeah. So I think the answer is no, although I will show you my best attempt at that by the end of the talk.
Right.
So if you do the measurement the way that we did it here, the temporal resolution is like, 20 minutes, because we have to integrate enough signal to, to get good enough, signal to noise and so forth. But there is a way to get much better temporal resolution down to, nanosecond range. Still not better than that, but I think down to nanosecond range, if you have repeat measurements. So if you can't do this like as a single shot, but if you have like a periodic thing, like from a pulse laser or something, then you can do something that's called step scan in Fourier transform spectroscopy. So essentially, the idea in step scan is you're taking a spectrum with a Fourier transform spectrometer, right? And normally, what's happening is the interferometer is just like wobbling back and forth at all times. But the idea of step scan is you sit at a particular mirror position and you do whatever measurements you need to do, and you can use a lock-in amplifier, and you can have a pulse measurement, whatever, and then you can shift to a different mirror position, and then you can do that again, and you can shift to a different mirror position, and you can do that again. And in that case, you can time gate your detector, or probably time gate with a chopper would be easier. And then you can get down to maybe few nanosecond, 10 nanosecond type resolution. But still, I don't think that gets you to what you're asking about.
Yeah. Okay. Well, thank you. That's interesting.
Yeah. Anybody else? Okay. So that's kind of this first technique that I wanted to show you, depth thermography. So the second technique I want to show you, that's a kind of a new way to measure thermal radiation, is to me very amusing. I'm amused by this. And in fact, we demonstrated this for the first time. The postdoc in my group demonstrated it in his apartment while we were on lockdown when COVID hit. So between March and June, we were just in complete lockdown. We couldn't go to the office or lab or anything. And he took some equipment home and actually set this up and got it to work. I think right around May or June for the first time. So the idea here is, can we do spectroscopy without a spectrometer? So for example, every spectrum that I showed you before, we used a Fourier transform spectrometer, like an FTIR. It's a very common instrument for measuring thermal radiation. But of course, there's many other spectrometers. So there's grating spectrometers and old school prism spectrometers and so forth. And all existing spectrometers use some sort of optics to achieve spectral selectivity. So some sort of element that disperses the light in some way, and gives you the ability to read out a spectrum. So for example, if you have a grating or a prism, your light comes in and the grating spreads it into different directions so that the wavelength corresponds to a particular direction, and then you take off the light over here and you're measuring a spectrum that way. In a Fourier transform spectrometer or another type of interference spectrometer, you have, for example, some sort of multiple beam paths, in this case 2 beam paths, and you're changing the interference condition with a moving mirror. So I'm sort of assuming that this entire thing is kind of somehow a dispersive element. It behaves differently, as a function of wavelength, depending on some sort of mechanical motion. You can imagine doing the same thing with like a Fabry-Perot interferometer with a tunable mirror, or you could have a single detector, but you could have like a tunable filter in front of it, or a filter wheel, or an array of detectors with different responses and so forth. So all of these use some sort of optical component to achieve spectral selectivity. And I'm going to show you in just a second that we can measure a spectrum without using any optical component that provides any sort of dispersive effect, like with all of these other methods. So how do we do this? So the way that we do this, and we call this technique Planck spectroscopy because it's based on the Planck's law of thermal radiation. The way that we do this is experimentally very simple. We take our sample, we put it on a heater stage, we put a detector in front of it, and we measure what the detector is seeing as a function of the temperature of the sample. That's it. That's the spectrometer. So how does this work? So the unknown thing that we're measuring the spectrum of here is the emissivity. So we assume that the sample has some sort of emissivity spectrum. This is emissivity that's a function of wavelength, and maybe it's like this, maybe it looks like this, maybe it looks like this, whatever. It's some sort of unknown emissivity. We discretize that emissivity, right? So we say that the emissivity is something at the first wavelength, something else at the second wavelength, something else at the third wavelength. That's this vector over here. And the measurement that we're doing at the detector is a power versus temperature measurement, right? So we're measuring the power at one temperature, the power at another temperature, the power at a third temperature. We get this plot of power versus temperature. Here I'm normalizing the power by temperature to the fourth because it's the kind of the Stefan Boltzmann normalization. And so you can see that essentially the power that you're measuring versus temperature, these curves are different depending on what the incident intensity is. And the reason, of course, that that's expected to be the case is because of Planck's law, right? The Planck's law of thermal radiation, the spectrum changes as a function of wavelength, right? And so you can kind of view Planck's law itself as being a tunable filter, right? At different temperatures, Planck's law allows different spectral components to come out at relatively different magnitudes from the sample. And so what you can do is you can essentially frame this as an inverse linear algebra problem, where you say, hey, I know what my measured power versus temperature is because I've done this measurement. And I know what this matrix is because it's literally just Planck's law versus wavelength for all these different temperatures. It's literally just the matrix of discretized Planck's law. And you know that this emissivity multiplied by this black body matrix is going to be equal to this vector of power versus temperature over here. And so if you know these two things, all you need to do is apply some sort of inverse problem method to get the emissivity. And so that gives you the ability to measure a spectrum without using any grating or prism or FTIR or anything else. Now, I should say this is a very poorly conditioned problem. And it's difficult to do this inversion, and you have to use some constraints and so forth. But we were able to do that, and this is currently sitting on archive. It's not yet published, but it is in peer review. And so I wanted to show you that this, in fact, works experimentally. So here is the experimental setup that we used. So this is a sample, so again, sitting on top of a temperature stage, the same temperature stage that I was showing you before. The temperatures that we're using here to do the measurement is 190 Kelvin, sorry, to 520 Kelvin. So it's a pretty nice and broad range of temperatures. And we put the sample down on the heat stage over here, and we have a window so we can purge it, because if you want to go down to way below room temperature, you don't want condensation. So we just purge it with dry nitrogen. And then we can either put a sample there or we can put a black body reference there. And we take that output and we just send it to an infrared detector. I'm using a lens here. In principle, the lens is not necessary. You could just put the detector really close to the sample, but we decided to do it this way, just to make sure that you don't have like some weird conduction or convection from the sample to the detector. So we just put it really far away, and we built like an imaging system. And here's the experimental results. So this is the voltage on the detector and versus the temperature for a bunch of different samples. So we have the black body sample, and then we have a bunch of test samples that we wanted to use to do these measurements. So we again used our polished fused silica sample. We used a sapphire sample. We used a doped silicon wafer with a phosphorus doping at a level of 10 to the 20 inverse cubic centimeters. And then we used a different silicon wafer with phosphorus doping of 10 to the 21 inverse cubic centimeters. So the first thing we did is we put the black body reference here, and we wanted to calibrate our setup. So essentially, we started out saying, we don't necessarily know, for example, the responsivity of our detector versus wavelength. And so we need to know that to be able to do this kind of measurement. So this is what this plotter is over here. Essentially, we're using this Planck spectroscopy technique, this inverse problem, to figure out what is the responsivity of the detector multiplied by the transmission of the lens, for example, in the window over here. And so what we get in the symbols is the extraction algorithm. After the extraction algorithm was applied, this is the spectrum that we measure. And then the solid line, which we call provided, is essentially the responsivity spectrum of the detector provided to us by the vendor. So we just looked at the spec sheet, multiplied by the transmission of the lens from the vendor, multiplied by the transmission of the window from the vendor. And you can see that they overlap very well, I think. So I was very happy that this Planck spectroscopy technique is in fact able to capture the responsivity of the detector. And after we did that, we then used this responsivity of the detector together with this experimental data for all of these other samples, and we inverted to obtain their emissivity spectra. And so, for example, here is our sapphire, and you can see in the symbols the spectrum that we recover. And here's this fused silica wafer. By the way, this feature over here in the fused silica wafer is a result of two vibrational resonances that are optically active. So it's kind of optical phonons, but this is an amorphous material, so it's maybe a little bit hard to call it phonons, but regardless, it's vibrational resonances. They're kind of the Reststrahlen band of the material over here. And so these fit very well. And then if you take a look at the emissivity of this doped silicon wafer, where you have like a plasma resonance over here, then you're able to recover that pretty well. And the same thing with the higher doping density. And so roughly speaking, we have a resolution of about 1 micron in the mid-infrared, and we're able to do this, again, without any sort of prism or interferometer or anything else. It's just purely based on Planck's law. So we thought that was kind of a cool way to do spectroscopy. And we're also potentially excited about this method because we think that it can turn like a regular infrared camera that just uses an infrared detector array, it doesn't have like a spectrometer or anything else, and turn it into a hyperspectral camera, because essentially at every pixel you can do this kind of treatment and you can back out what the spectrum is of, for example, a scene at every point on the scene, or for every detector pixel. So we'll see. We haven't done that yet, but that should be possible based on this kind of approach. Any questions here or comments?
Are there any kind of caveats to this? So it seems like there's a specific temperature range that you're kind of looking at, right? So it's close to room temperature and above. What happens when you like really cool down?
So I mean, thermal radiation is proportional to temperature to the 4th in Kelvin, right? So the lower you go, the less signal you have.
I see.
Right. So essentially, when we get down to below, this temperature, the detector that we're using here, this MCT detector that we have in the lab, just isn't picking very much up anymore.
I see.
And so, that's kind of our limitation. There, in principle, you could go up to very high temperatures. You can imagine going up to thousands of degrees, right? And doing measurements at much shorter wavelengths, because of course you're getting a lot more signal at shorter wavelengths if you go to very high temperatures. We don't want to melt any samples, and also the bigger your range of temperatures, the more likely it is that your emissivity actually starts changing as a function of temperature. And then there's pretty much no way to simultaneously extract like a temperature tunable emissivity using this kind of approach, and the spectrum of the emissivity kind of at the same time, just because you don't have enough data to be able to do that inversion at the same time.
Okay.
It's too many degrees of freedom that you're trying to fit.
Well, yeah, that's right.
So,
okay.
So this is kind of the range we used. You could certainly go higher. You can easily go up to like 800K for most materials, but this is what we happen to use.
I see.
All right. Oh, I have a chat. Oh, okay, that's Chiji leaving. Okay. Yeah, thanks, Chiji, if you're still here. Thanks a lot for coming. So, all right. By the way, I mean, I should say that even though I just said that you can't do this for emissivity that changes as a function of temperature, there are kind of modified approaches that you could use that would enable you to do those kind of measurements. So here's kind of like a modified Planck spectroscopy measurement, where instead of using one temperature stage and your sample, and you're using the thermal emission from the sample, you could have two temperature stages, and you could have your reference with the known emissivity be sitting on the temperature stage, and you could like reflect off of the sample or transmit through the sample. And in that case, you're doing something that's quite similar to some sort of conventional spectroscopy. You can imagine putting polarizers here and do kind of ellipsometry type measurements and so forth. And in that case, you can, of course, handle temperature-dependent emissivities as well. In this case, reflectances or transmittances. But of course, the more you build up kind of instrumentation, the more you get away from this ethos of kind of the world's simplest spectrometer in terms of the number of optical components, and then kind of the less maybe interesting this gets. But still, this is a nice possibility to, for example, do kind of hyperspectral imaging in the infrared, where hyperspectral cameras are incredibly expensive, something in the range of $500,000 to $1 million for a good hyperspectral camera. Whereas here you can imagine putting like just a regular off-the-shelf, $5,000 infrared camera over here and doing these kind of measurements and getting a spectrum as a function of position, which seems potentially interesting. Okay. So, all right. So that's kind of the end of my methods. So how am I doing on time? I'm actually not doing that well on time. Let me. How much more time do I have?
Maybe like 10 more minutes, maybe.
Okay. So let's see how far we get. So now let's talk a little bit about engineering, because I think that's interesting as well. So I told you earlier that the emissivity can depend on many things, and it's very normal and common for the emissivity to depend on wavelength. This is something that we see all the time, but it can also depend on many other things. And in particular, it's interesting to consider objects which have a temperature-dependent emissivity. And if we have an emissivity that is temperature dependent in a significantly strong enough way, you can get some anomalous behavior, like, for example, non-monotonic thermal emission. But if we want to do that, then you need materials with temperature tunable optical properties, and therefore temperature tunable emissivity. And so what we've been doing over the last 5 or 6 years, or more even actually, is we've been collaborating with a number of groups, most notably with Shriram Ramanathan's group at Purdue University, who are experts in synthesizing and analyzing these complex oxides with phase transitions. And we've been working with some of these materials. So kind of the famous one, the canonical one, is vanadium dioxide, which is a metal oxide that has an insulator to metal phase transition around 70 degrees Celsius, which results in kind of dramatic changes in DC conductivity, in the crystal structure, and the band structure, and also in the optical properties. But we're starting to look at some other materials as well. I'll show you one in just a second. In the case of VO2, the complex refractive index in the infrared, which is where we kind of care about, changes really dramatically going from room temperature to high temperature. So this is from 30 degrees Celsius, for example, to 100 degrees Celsius. These are spectroscopic ellipsometry measurements that we did at UW-Madison from about 200 nanometers up to about 30 microns. This is incredibly broad. And actually, if you're interested in using this data for your own kind of design and simulations and so forth, you're welcome to check out this paper we published in 2019, which if you go to the supplementary information, you have the full data set. You can like copy and paste it into any of your electromagnetic simulations, for example, because we couldn't find these data sets. And so we made our own for for VO2 kind of as a function of temperature throughout this phase transition. And you can see that the change is very, very dramatic. And in fact, the material goes kind of in the mid-infrared from being a kind of a low loss kind of dielectric type material to being like a really bad metal. That would be, what you would call this. And then, early on, this is actually while I was still a graduate student in Federico Capasso's group, we did our first kind of measurement of this type. This is before we had the fancy calibration of thermal emission measurements that we have now. But here is kind of the emitted power versus temperature of just a thin film of VO2 and sapphire. And you can already see that this is very, very strange, right? So as you increase the temperature, the emitted power goes up, and then it reaches a maximum, and then it goes back down, and then eventually it starts recovering back up again. And so if you look at the samples with an infrared camera, so this is 6 snapshots taken with an infrared camera, you can see that like at 75 degrees Celsius, the object looks like it's a lot hotter than it looks when it's at 85 degrees Celsius. So this is very, very strange, but the reason this happens is because essentially the emissivity of this VO2 and sapphire drops dramatically as a function of temperature as you encounter the phase transition, because the optical properties change so much. And so then you have this kind of dramatic effect. And we thought that was quite interesting. So after we did this, and after I moved to UW-Madison, one of my goals for kind of my research program at UW-Madison was to essentially try to conceal the information that's carried in thermal radiation. So our goal was to create a thermal emitter that has kind of a many-to-one relationship between temperature and thermally emitted power. So before I kind of was showing you that a spatial gradient of temperature maps to a spatial gradient of thermally emitted power. That's how infrared cameras typically work. And I wanted to break that. I wanted to make many temperatures map onto just a single thermally emitted power, kind of, so that you wouldn't get any information from an infrared image of this type. And so fundamentally, what we're looking for is a plot of thermal power versus temperature, which is like a horizontal line. And that's why we call this a zero-differential emitter, because we want this to have no derivative. And so the way to do that, right, in terms of the Stefan Boltzmann law, is to have an emissivity which decreases as temperature to the fourth, right? So this should have something like T to the -4, so that the whole thing ends up being a constant. And so fortunately, we were able to do this, and we're able to implement this in 2019 in this paper in PNAS, based on another material with an insulator to metal phase transition. In this case, we're using a rare earth nickelate, samarium nickel oxide, which has a very complicated insulator to metal phase transition at around 100 to 130 degrees Celsius. A phase transition which, quite frankly, I don't understand, because it's I'm not sure anybody does very well. It's kind of incredibly complex, with a very complicated mess of the various degrees of freedom in the material that results in this kind of Mott-like physics. But I'm an applied physicist. I just get to use it once it's there. I don't necessarily have to understand everything that's happening under the hood. And when we did a spectroscopic ellipsometry to kind of characterize the optical properties, we saw that the optical properties changed, like in the case of VO2, quite dramatically, but not nearly as dramatically as VO2 as a function of temperature. And that was exactly what we needed, because what we needed is to have this emissivity which changes with temperature in just the right way to cancel out the temperature dependence of the Planck and Stefan Boltzmann laws. And so we were able to do that. And so here is a result from this PNAS paper in 2019. This is the integrated radiance, integrated over wavelengths versus temperature. And you see this range over here for the zero-differential emitter, this surface with samarium nickel oxide on top of sapphire, where the curve is flat, right? So this is what we were looking for, the radiance which doesn't change with temperature. And you can see evidence of this with infrared imaging. So for example, if you have like a sample over here that's just hanging off of our temperature chuck, over here it's at 130 degrees, and over here it's at a much colder temperature, about 90 degrees, just because it's hanging off of the chuck, like air cools it down. And so if you take just like a typical wafer, here it's a piece of sapphire, you can immediately see this temperature gradient on an infrared camera. Whereas over here on the zero differential sample, you don't see anything at all, because essentially, even though this place is hotter and this place is colder, this place has lower emissivity and this place has higher emissivity to kind of balance that out. And this happens automatically. And so you end up essentially having kind of no spatial information for this infrared camera. And so, we think this is kind of interesting and exciting from like a kind of a infrared privacy camouflage type application where we can try to conceal things. So I'm almost out of time. And so I just am going to show you one result in about 2 minutes, and then I'm going to wrap up. which is that in addition to looking at emissivity as a function of wavelength or as a function of temperature, we also took a look at emissivity as a function of time. And the experiment that we did was this a kind of optical pumping experiment in collaboration with Alberto Piquet's group at the Naval Research Lab. The idea was that we took a piece of undoped semiconductor, like just a wafer of gallium arsenide here, or a wafer of silicon. We put it on a heat stage, here at 200 degrees Celsius, and we took this infrared detector over here. And normally, this sample doesn't emit very much infrared light because the emissivity of like an undoped gallium arsenide wafer is almost zero. And then you hit it with a pump pulse at a wavelength that's much higher, much shorter than the band gap of gallium arsenide, and you generate a whole bunch of free carriers, right? And then because you generate all these free carriers, if you calculate like the Drude response of the material becomes quite lossy in the infrared, and your emissivity goes way up. And so then your thermal emission power goes up. And then the carriers recombine, and the emissivity goes back down again, and then your thermal emission power goes back down again. And so essentially, we're able to observe this emissivity modulation on a time scale of about a nanosecond or a couple of nanoseconds. And to our knowledge, this is actually the fastest ever modulation of thermal emissivity by something like a factor of 1,000. And so also, this is an interesting and unique way of generating infrared pulses from visible pulses. So normally, if you want to generate, like, turn a visible pulse into an infrared pulse, you use like some sort of parametric amplification or an OPO or something like that. And here, we don't do that, right? We don't have a parametric oscillator or anything else, not a conventional one at least. We just have a wafer of semiconductor at a temperature that's 200 degrees, and you hit it with the visible pulse, and an infrared pulse comes out. Of course, this is not an efficient process, and not a coherent process either, but nevertheless, it is a new way of generating infrared pulses that I think is interesting and is also very fast modulation of emissivity. Okay, I'm out of time and I'm also out of topics. So I'm going to just leave my outline and summary slide over here, and I'm happy to take any further questions. Thanks again, everybody, for joining the talk.
Thanks, Mikhail. That was a very interesting talk, and it seems like you really kind of went into the bowels of trying to really understand thermal emission. So please, if there are any questions, please just unmute yourself and ask a question. Especially encourage the students to ask questions. Perhaps let me begin. So you had one slide, maybe like 3 slides ago, that said something about doing something non-linear with, just one more slide before that. Yeah, that's right. No, yeah. So what was this thing about?
Yeah, sorry, I went through this.
The nonlinear optics.
Essentially, all I wanted to say is that normally when people think about frequency conversion, they think of like nonlinear optics, right? They think of
second
an OPO with some nonlinear crystal and so forth. And this is like a completely. All I wanted to say is that this is a completely different way to kind of frequency convert a pulse, for example, a pulse of light, right? Where you send in a visible pulse and out comes an infrared pulse. And this is absolutely not based on like a nonlinear crystal of some kind, or even though I guess it is technically a nonlinear process in some kind of narrow way.
Nonlinear.
Yeah. I mean, strictly speaking, anything that changes frequency, I guess, is, well, I don't know if you, maybe not. I guess there are linear frequency conversion processes, but like this is a nonlinear process because it does depend nonlinearly on the pump intensity, but actually it depends on the pump intensity and the pump pulse intensity in a very non-trivial way. That's not necessarily difficult to, not necessarily easy to predict either. So it's just like a very different way of doing frequency conversion and nonlinear optics, in this case, based on kind of dynamically modulated thermal emission. By the way, what I kind of described here is a very naive picture. There's actually much more complicated stuff going on. And if you take a look at the supplementary information of this paper in Light Science and Applications, we spend a long time building like a pretty complicated multi-physics model because for example, this is actually one of the cases where the lattice temperature and the electron temperature are very different for a short amount of time, because the first thing you do when you hit it with this pulse, these are very kind of high energy pulses, and very short, just hundreds of femtoseconds, you actually end up heating the electrons up to like up to I think about 4,000 degrees, and whereas the lattice remains at about 200 degrees Celsius, and so you actually have this kind of multiple temperature object, and it's really only the free carriers that are emitting. And we did account for that when we built our models, so I didn't talk about this, but this dotted line over here is a model that kind of models what's going on in all of these cases. And in fact,
carrier cooling or something? Is that what?
Yeah. So you have carrier heating and then carrier cooling, and all of that is hidden. Actually, there's a very, very large sharp pulse that happens on a time scale of about 1 or 2 picoseconds here in this material, but you don't see it because the detector responsivity is only about 1 nanosecond. So it's like hidden in this. It's hidden in this peak. So this peak is actually not supposed to be this big. Just from the change of emissivity, it's supposed to be only about this big, but it becomes bigger because you have this very, very short, kind of picosecond scale pulse that we can't measure in this kind of stuff.
That's just being convoluted by the response function of your mid-IR.
Exactly, right. So you could deconvolve, I guess, but I don't think you can deconvolve a picosecond feature from a nanosecond.
I see. So actually, things like this happen in graphene all the time. So there's it's a paper, for example, if you kind of blast graphene, it gets heated up to, I don't know, like 3,000, 4,000, 5,000 kind of Kelvin, and people actually observe black body radiation coming out of it.
Yeah, so I know the papers you're talking about. I think from Columbia and from some other places. Yeah, so that's actually the one place that I've seen that also tries to kind of directly measure thermal radiation from in the same kind of way. It's interesting because I think that work has the record for the fastest modulation of thermal emission, even though they don't really talk about it in those terms. But we have the record for the fastest ever modulation of thermal emissivity.
Yeah.
And the reason is because in graphene you have this. I don't remember what the carrier cooling time is in graphene, but it's certainly faster than like a nanosecond. And so you're able to get this very. And I think it's faster than a picosecond as well, which is what we have here. Do you know what it is?
So it depends. It depends from sample to sample. It depends on temperature. The typical things around 3 or 4 picoseconds. If you go to lower temperatures, you can go as long as 10, 10, 20. At higher temperatures, it's something like 1 sometimes. If you're on HBN, it can even go down to 500 femtoseconds. It depends on the situation. Yeah.
Yeah, I'm embarrassed that I don't know this, because actually when I was an undergraduate at Cornell, I worked in Farhan Rana's group.
Oh.
And I was.
I won't tell him that.
Sorry?
I won't tell him then.
Well, so I worked on semiconductor optical amplifiers there. So at the time there were kind of 2 parts to the group. One was kind of on semiconductor optoelectronics, and one of them was on pump probe spectroscopy of graphene and things like that. And I didn't work on that at all. But like by now, I think that group has transitioned almost entirely to those kind of pump probe measurements. So I'm a little embarrassed that I don't remember, but I was an undergrad, and I blame ignorance. But yeah, so they're primarily looking at temperature differences, whereas for us we have both temperature differences and emissivity differences, and the emissivity differences are quite dramatic here. So that's kind of the aspect of this work that's a little bit different.
Great. So Paul seemed to have unmuted himself to ask a question, but he just kind of muted himself again. So Paul.
Yeah. So yeah, you basically answered the question along the way. It was a similar question I had before about timescales of the relaxation, and so you answered that nicely. Thank you.
Yeah, so I'm showing you here gallium arsenide, just undoped gallium arsenide, which the carrier recombination time is just about 3 nanoseconds or so, and that's really what guides this decay. We also did these kind of measurements on undoped silicon, and then you have much longer decay time. So the pulse looks like this, has like this very, very long tail. And you can imagine playing all sorts of games, right? You can dope, and that changes the relaxation time, the recombination time, I should say. And you can play all sorts of games. We did not here, but
yeah. Thanks.
All right. More questions? Yeah. So one more question for me.
Yeah, I apologize. It's not exactly a classical condensed matter talk. So
No, don't worry about it.
maybe out of the wheelhouse.
No, this was interesting. So I had one more question. So in terms of this Planckian spectroscopy, you're really doing just an inverse kind of problem, and that really depends on the fact. Actually, this is a great slide. Yeah, that slide there. The fact that these samples are emitting a kind of normal Planckian way, right?
Well, I mean, normal Planckian way multiplied by the emissivity, right?
Yes, that's right. That's right. Sure. But what happens if you have a whole bunch of, say, phonon modes that are kind of there? Is that screw things up?
No, not at all. I mean, so that's all accounted for in the emissivity. That's what you're looking for. So for example, fused silica has a vibrational mode at about 9 microns and another one at about 8 microns, and that results in this emissivity, spike over here in the emissivity spectrum. And that's what this thing is measuring, right? This technique measures, all of that stuff. So the only time that this would result in some sort of weirdness is if each one of those modes had like a different temperature or had an occupation that's at a different effective temperature, and then that would mess this kind of technique up. But under normal circumstances, no, I mean, that's totally fine.
So what constraints on the emissivity? So I guess the emissivity captures everything, but then there's some constraints on the types of emissivities that you can measure.
Yeah. So
is the constraint basically this temperature thing? So they all have to be bosonic modes that they don't have to be bosonic modes. They just all have to the same temperature. Is that the point? So that you can.
Yeah. So certainly we assume that everything is at the same temperature. We assume kind of thermodynamic equilibrium of our sample. If you don't assume that, then you can't define it in a single emissivity in the first place. And the other assumptions that we're making when we're solving this inverse problem, one of them is that the emissivity has to be between 0 and 1, because that comes from thermodynamics. And then the other assumption that we made here is we assumed that the emissivity didn't change too fast with wavelength. So I think we made an assumption that the emissivity didn't actually change, wasn't going back and forth faster than about a micron, because we sort of, just by playing around, we realized that the technique couldn't resolve anything be smaller than a micron anyway. And so it turned out that it was easier to do that inverse problem that way. Quite frankly, we're not like good enough applied mathematicians to solve this inverse problem the best way possible. We kind of used like a linear equation solver in MATLAB and just tried a whole bunch of different things and eventually found,
that's okay.
Found a way to do it. So I think you could, sorry?
It's pretty optimized in MATLAB, right? So it's
okay. So maybe we did it as well as you could possibly do it. I mean, my guess is somebody doing some sort of neural networks or something could probably do a better job, maybe. But yeah, those are actually the only constraints that we put on here. You can, in principle, do a lot better if, for example, you assume some sort of shape for your emissivity. So, for example, if you assume like some oscillator model, if you say, look, there's like 3 vibrational resonances and 1 like Drude oscillator, and then you just instead of varying the individual like emissivity at every wavelength, you could vary like those oscillators. Then you have fewer degrees of freedom, and it's easier to do the fit. So you can imagine doing better than this, I think. We were pretty hopeful about the fact that even in this kind of rather difficult problem where we're really trying to resolve each wavelength kind of individually at a relatively at a relatively decent resolution, we're still experimentally able to this isn't like fake data, right? This is actual experimental data, and we're still able to get a spectrum. So we could probably do better.
I see. Great. I don't see any more questions. Are there more questions?
Don't be shy.
Don't be shy.
Questions are welcome.
Yeah, especially students, or if the faculty want to ask some questions, that's fine as well. You can pretend you're a student, and that's okay. That's what I always do. No, last call. All right, so since there are no more